Thank you. Thank you for the opportunity. Today is one of those rare talks where actually I get a chance to speak of something I'm really passionate about, which is the teaching aspect of my work. So I'm going to talk about how do you scale your science, and more importantly, people, and I'll explain why I mean people. Now, this title is not exactly what I wanted. It so happened that Jason and I were talking, and I said, I should say something about this, and then I didn't answer any of his emails, and then this became the title, and I couldn't change it, so I'm sorry, but I learned to answer my emails more quickly. So my motivation to teach cloud, and I really want to go into the details of why, and I'm talking of more than 10 years ago and 2006 as well, as to why I started including cloud in what we were teaching. And then pragmatic approaches, both as a cloud provider, so my projects have systems where we build clouds, we give them to people, these are managed clouds, and then I go consume them, not just with what I have, but what other people have, including what Phil's making available. That's the sort of the background and what pragmatic concepts you have to give the students so that they can, or researchers, so that they can effectively use it. And then some very specific coursework that others, not me, but others that I know that utilize our cloud infrastructure and how they are doing it. And then finally, the course that I teach, and how do you include sort of complex application stacks as part of your coursework without sort of moving away from the science. And that's always a challenge. You know, how much time do you spend teaching technology, and how much time do you spend sort of teaching the science and interpreting the results, and how do you strike a balance? And I'll show you about 5 years of experience of how we have done that, and some future directions if we have time. If not, we'll piggyback on the end of the session. So my motivation for teaching the cloud started sort of early 2000. The course that I was teaching at that point, and actually I see some familiar faces in the audience from that course, is that more and more of our students were getting either postdoc or faculty placement at academic institutions that did not have HPC or even any computational infrastructure. And we were training them to be computational biologists, and yet they were getting placed in places where they were going, and the only thing they had was a tiny lab with a PC, or in many cases, just about nothing. At the same time, University of Arizona had a bunch of IGERTs, PERT postdocs, and they were working with community colleges, they were working with PUI, primary undergraduate institutions, and they didn't have any of this. And I personally took it upon myself as sort of a workforce development aspect, where if we were going to do something for training somebody in a community college of how to be the next generation lab technician, they had to know computation. And if they didn't have access to this, most likely they were not going to be more effective. And this also applied to our undergraduates who came to our lab. If they did not know the fundamentals of bench skill or hygiene at the bench skill, they would not know data hygiene on the computational side, and we would get bad results one way or the other. And the new postdocs and faculty really wanted to operate at scale, and in around 2000, as we all know, the scale was really going up. And so instead of sort of playing with toy data sets, the idea was, I want to work with real things, and how do you make that possible? And so owning infrastructure was not possible. If you have a primary teaching institute, you cannot, from your startup package, afford someone who's a sysadmin or space or whatever it may be. And I would say the most important thing was computational thinking had become central to our coursework, which is sort of the abstraction, automation, and sort of the audacity and ability to scale that was being taught in all our computational work. Around 2006 is when Amazon officially came out with AWS, and there was an opening for us to use on-demand resources. Now, keeping in mind at Arizona, I had enough HPC resources, and our campus is very fortunate, and we refresh technology every 3 years, and our budget's in a few $1 million a year for that. And so the students are fortunate. Even an undergraduate can get access to those systems, even in the 2000s. But this allowed people who left us. And then finally, NSF funded iPlant in 2008, which sort of gave me the sort of soapbox, if you may, to start saying that we need to make this more widely accessible, and infrastructure is beyond institutional boundaries. Because every institution that owned some of this infrastructure, you had to be a member, you had to have those single sign-ons, and the moment your student graduated, they were pretty much cut out, and you could never collaborate with them. And we had realized that this collaboration spanned a time frame that's way beyond your graduation, and these are long-term relationships, and you had to go back and forth. And so this was sort of the start of that. Scaling users and building communities is sort of where my focus was. And so most labs have an in-house computational guru, someone who's good at some of those things. They produce the custom code, they develop the pipelines, they investigate new methods. Occasionally they teach others how to use that, but most of them, through osmosis of different kinds, pick it up and start using it, and that becomes a lab protocol. And typically those people are victims of their own success, and there's a denial of service. Everybody wants them to do something during a conference or a paper, and that group of people are usually really unhappy because they are N of 1 or at the most 2, and the demand is really high. And then the PI goes to a meeting, hears about something, presents their work, and gets 3 new collaborators, and now you dump something on the lap of that same person, and the denial of service continues. And then finally you get irritated and you say, I'm just going to have you install this on your cluster, and most likely your code is not going to work with them, and then you end up arguing with them, and then finally you're already under stress, and now you have to take care of somebody else's system, and so you either decide to just leave the whole thing and become a monk, or I don't know what you would do. And then the faculty, this was really motivating for me. Faculty were wanting to teach hands-on topics in course and workshops, and the complex application stacks were getting in the way. As we were getting into NGS and more deeper image analysis, the amount of libraries and custom environments, which is growing, and people were not teaching those because it would take a day just to set something up. So there was the ripe opportunity to do something, and it literally took away from the focus of what the intention was, and we were discussing technology plumbing, which I love, but that's not the focus. Just to clarify, how much time do I have left? Because the slides I really care are towards the end, so I have 10 minutes, okay. So this is sort of what our users are typically looking for. That's what they want. And then we end up sending them to Home Depot and say, oh, you want that? It's all there. It's at Home Depot. Go get it. And that's what I compare to sending people to the cloud. You want to do your analysis? It's right here. It's in the cloud. It's in Amazon. Go get it. And you tend to completely overlook what's required for identity management, what's required for data management. There are lots of other components that go in to effectively using the cloud. And then when you send people to Home Depot to build furniture, you end up getting this, you end up getting this, and finally this is sort of how you would say happy birthday to IKEA, and that's what we are doing to our users and saying, here's your birthday cake in the cloud, enjoy it. We sort of also have to understand what is expectation management in the cloud, okay? How many of you have sort of cable TV? Okay, that's good that you raise your hand when you expect a channel and you expect to record a channel, okay? Cloud's more like this. There is no channel. You see what you want, but doesn't mean it's all rosy. You start seeing things like this, and you have to be prepared. And the problem I have, which is the serious problem, is that cloud has convinced people that there are no problems. It's just completely peachy, rosy, and it just good things happen, and that's not the case. If you ever get a chance, go talk to someone who is an engineer in a cloud infrastructure. Doesn't matter, Azure, Amazon, they will tell you, and there are beautiful talks on, do not tell people the cloud's that simple and easy and nothing bad happens. It's on fire all the time. The difference being you don't see the smoke because it's far away. So, you have to be prepared for failure. Your idea of failure doesn't change whether it's under your desk or in the cloud. So, the next thing that sort of was really important for me was the paradigm shifted from producer to user innovation. And those of you who haven't read this book, I highly encourage. It's Democratizing Innovation. And Eric von Hippel, it's an open source book. He makes it clear that people who suffer the most are uniquely equipped to solve a problem. And in this case, our users, our researchers were suffering the most, and they didn't really have the tools and bits to make it happen. Cloud was sort of the first time where the tools and bits were in their hand, and instead of it being Home Depot, there was an IKEA box with some instructions that they could use. And so check this book out. And so in Cyverse, when we realized that Amazon in 2006 was doing something, and there was an opportunity and others were coming around, we needed a managed cloud, not just the resources, because most people do not know how to effectively use the cloud. And what you see today is going to be different in a week because there'll be new capabilities. And so you have to be willing to know what is the new things that are coming around. So we created Project Atmosphere. The idea was we were agnostic of the underlying cloud. We wanted to bring in the concepts of resources, managing those, allowing you to have allocations, and understanding what your consumption model looks like, have an app store so that you can share your app with others. And so we did that in the early 2000s, or actually more mid-2000s, sorry. And this is how it looked. And then we realized whatever resources we threw at it, people just consumed and gobbled it, and we were out of physical resources. And the instant answer or question was, oh, the cloud's unlimited. And my answer would be, it's limited to your credit card limit. So if you give me a credit card and let me do that, I'll give you unlimited resources as well. But the reality is you have to learn to live within those resources. So with NSF and a few of my colleagues, we wrote Jetstream, which is much, much bigger. And it's using the same software layers. And we can talk about that if anybody's interested. At the end, we were focused on empowering users. And unfortunately, none of my animations are working here, but that's okay. Here is an example of a user asking for resources, and this is very recent. It's in June, okay, for a workshop. And you can see that the content that they're asking for is very specific. They're teaching concepts that are important, and there are 30, 40 students in the course. And that's a common occurrence in our infrastructure. Faculty come, they want to teach a workshop, it could be wherever, and they start building these things. Just want to make sure people are clear about cloud computing. It's not a singular technology. It's not a black box. Scalability is important, and it's not just solving big data problems. There's a lot of hype. You have to be careful. And at the end, this is what I see more and more. It's like, hey, it's here. I just put it in the cloud, and good things happen. That's not easy. It's amazingly flexible. It allows many components to come together. We build purpose-built appliances, so that's where people create an image, and then they share it for a workshop or an SOP, standard operating protocol, for the lab, and everybody in the lab is using exactly the same methods. And if you update something, there's a new image, and that gets sort of superseded by it. And it opens a lot of avenues for people to design new coursework that normally would be very difficult to do if you were going the traditional route. This is sort of how we see our users, our students. The beginners are looking for a bigger laptop. It's just that they want to put it in the cloud. I need something bigger than my laptop. And they need admin or pseudo privileges to install something because local IT will not give it to them for good reasons, and sometimes not so good reasons. And then you have the intermediate users who are looking for custom components. They have some databases, they have some application servers, web servers, some pipelines, and they need to manage their workflow. The advanced users typically come in with some specific technology that they want to apply to their data. Very often it's misguided because they don't know what distributed computing is. And very often we ignore the many years of computer science where there are very good methods for distributed computing, and we just run after what internet companies are putting out. What Twitter puts out is for their kind of use case, and it takes about half a dozen engineers to run it. Doesn't mean you can do it just because it's in the cloud. So, some other things, and then a lot of edge computing where there are teams that are doing different things. This is what the landscape looks like, and we don't expect you to learn a whole lot if you try to just say, I want to learn cloud. And so don't get frustrated, be patient, be flexible, be constructive, and be creative. That's sort of where we go with this. So this is the course that I teach. It's called Applied Concepts in Cyber Infrastructure, or Applied Cyber Infrastructure Concepts. We cover distributed computing, we cover high performance computing, we cover data management, code management, virtualization, documentation, and team science. And at the end, you have interdisciplinary teams that come together. This is how it looks, and this is an actual sort of response we got from users. So the big red thing is I hate people. And I'm going to operate in the cloud by myself because nobody gives me any permission to do blah, blah, blah. After the course, they learn that to work as a team is important, and communication is equally important, and they don't hate people as much. So, and that's important when you're working with technologists. So it's a project-based learning course. These are the last 5 years. We started annotating a rice genome. We had to finish it in 24 hours for 12 genomes. Then we moved to groundwater-based simulation, then EEMT calculations, and then last year was the fun one with exoplanet hunting. That's when the astronomers showed up and they said, we also want to do this, and our coursework has nothing to do with bio. I mean, all the tools are agnostic of your domain. And so the astronomers said, yeah, we want to do this. And I said, well, come along. This year, we are focusing on the mapping of mosquitoes. So it's mainly Zika and dengue fever. And so that involves, all of these involve a researcher coming to us with a scalability question, and the students working to solve that. If they don't solve that, they don't graduate. It's that simple. They're going to get an F in the course. And there are teams, there are 5 teams that work on it, and they learn different things. And so they go from an idea to a solution in the cloud. Here's what we cover. You can see it starts with, the textbook is really simple. It's the fundamentals in massive data analysis. The researcher comes, presents the question. They learn about virtualization and Docker and some of the things, get good at command line. They learn cloud theory, and then they learn about Git, HPC, and then the workflow management systems. And then they start learning about web APIs and how we wire things together. They learn about data management. They learn a little bit about structured and unstructured data. We go and visit our campus HPC. We go and visit the campus networking infrastructure. And then they learn, what does it mean to route traffic? What is a 100 gigabit connection? Where does it go? And it really opens their eyes up as to they're sitting on possibly the best resources in the world, and then they start thinking how they're going to leverage that. We do some hands-on work, and after October to December, it's all projects that they have to weekly report, or every time they come to the class, they have stand-ups, they explain the progress, and they're interacting with the researcher. This is an example of this year's. Unfortunately, well, it is scrolling. So this is the GitHub repository, fits image normalization through distributed resources. I'm really proud what the students did. So this was presented at SPIE, which is a hardcore astronomy conference. This is Tyson, who is a field ecologist, who's presenting at Exceed, which is a HPC setup. Here's Asher, who is a genetics student presenting in a conference that is for astronomers, and this is like hardcore astronomers. And this is the email I got from my colleague saying that we learned enough from Asher about cloud computing, him being a genetics student, and so they made it all the way, So this is sort of what I like to see my users as, and this is the end of my slides, and this is where I like to take my students. So thank you. Yes.